Hello, my name is Rasmus Benestad.
I will talk about how global warming affects rainfall and temperature where you live. This is the first part of a two-part lecture. So, in other words, how can we estimate the consequences of global warming where I live? So basically, we want to have the description of the future climate. But the problem is that the global climate models that are our main tools for making future climate descriptions are not able to provide a description of the local climate. For instance, like the valley where you live, or like the mountaintop, or like the field in your backyards. The reason for that is that the climate models have a minimum skillful scale, and this is by their design. And I'll show some slides or illustrate that with some figures, which is shown here. So on the left here, you see a typical map of temperature from a global climate model. And on the left, this is the counterpart from what we call reanalysis. So these are basically weather forecasts with much higher resolution. You can actually see here the Nordic countries, whereas in the climate model is too coarse to actually provide the sufficient details to actually show the features of the mountains and the valleys and the local climate conditions. And we can see that here. So the local climate is mainly shaped by geographical factors as well as the climate of that region, which again depends on the global state. And you can see that here on this picture of these mountains in Norway, and you can see that there's actually snow in the high mountains here. And the reason for that is that the temperature is low enough so that the snow hasn't yet melted. Whereas you can see that in the lower part here, you can see that the snow is all gone. There's a little ice on the lake here, but that is also soon gone as well. So you can see by looking at the snow cover how the local climate varies from place to place. And of course, you could contrast this to a place like, say, in the tropics, which would look very different. So here you have a picture from Mozambique. You can see the Indian Ocean, and you have a much warmer, much more humid climate, and also you have more wind here because you're on the coast. Or you have, say, a place near the sea in the Nordic countries, which is also very different. So, and the way that the temperature, for instance, and rainfall varies from place to place is actually quite systematic. It's quite predictable. So you can look at this map here. This is the Earth, and then you can see that the different shades here are marked different mean temperatures. So you can see that typically you have warmer temperatures in the tropics and cooler in the high latitudes. Or if you roll this map out here, so you get like a rectangular map, you can actually see it easier. So you can see that you have lower temperatures in the mountainous areas. You have Himalayas here, and you have the Andes here, and Rocky Mountains. And also the temperatures are also governed by like prevailing sea currents. You can see it's warmer in Europe than other parts of the world with the same latitude and so on. You also see that with the rainfalls, you can see that there's a belt along the tropics here where you have most rainfall, and that sort of shifts with the seasons. And you can also see like high rainfalls in the areas where you have lots of storms. So this is the area of the storm tracks. You can also see that the temperature at, say, one place is correlated with the temperature in that area. And this map here shows the correlation. So the 1 is a perfect correlation, and -1 is a perfect anti-correlation. So You can see that the annual mean temperature in Oslo is very strongly correlated with the temperature in this larger region here. So once you know the temperature over Northern Europe, and then you also can estimate the temperature in Oslo, because these are part of the same feature here. You can also see that there are other places on the planet where you have correlations. But the fact that you have this connection between this large scale and a local scale means that you can apply some downscaling. And downscaling is basically the process of using information about how the local rainfall or temperature depends on the local geographical factors and the large scale climate conditions. And then you know how the large scale conditions are changing, because the climate models are able to actually simulate that. Then you can actually infer how that is going to affect the local temperature or rainfall. So here is one illustration of what downscaling actually implies. Is actually adding new information. So you have the global projections from the global climate models, and they have a skillful scale, so they can simulate certain parts which have sufficiently large scales. And then you can make use of the information of the dependency between a large scale and a small scale, because these are related. They're governed by physical processes, so they can actually you can see it in the statistics as presented here. And of course, you also have the geographical factors which modify and affect the way the local climate is changing. But there are several different approaches when it comes to downscaling. So you have, for instance, the regional climate models, or RCMs. They are used in something we call dynamical downscaling, which is sometimes also referred to as numerical downscaling. This is the main emphasis of the World Climate Research Program, the WRCP, and in the coordinated downscaling experiments known as CORDEX. And also you have a different approach based on empirical dependencies and statistical techniques, and this is known as empirical statistical downscaling, or often referred to as just statistical downscaling. We often use the abbreviation ESD to when we talk about empirical statistical downscaling. So just to have a look at the regional climate models, they are computationally demanding. There are a number of different RCMs with different options, so they are not the same, but they have similar sort of core design, but they have many different sort of choices and so on. These models provide a complete picture within the volume that they represent. So you get, say, the temperature, you get winds, you get the humidity, you get various, like all aspects that we can observe. But you also need observations for evaluation of these models, because they have some biases and they are not perfect, so they have some limitations. And you can also visit the CORDEX website here if you're interested to know more about these regional climate models. And here's one example of like one domain over Africa. When it comes to empirical statistical downscaling, basically this approach requires good quality observations and long records. And often the observations are scarce, and sometimes you also struggle with the quality as well. And then you also need a good understanding of the local climatology and also understanding of statistics, because it is easy to apply a statistical method which is not very suitable and get some bad results. You should also find, when you do this type of downscaling, you should actually, it should make physical sense. It should confirm your physical understanding of what is going on. Empirical statistical downscaling is computationally cheap, and is suited to apply on large multimodal ensembles. So you can apply it to all the GCMs that you have. You can do it fairly efficiently. So you get scenarios based on many global simulations, and you can capture like natural variability and also decadal variability. Another nice thing with empirical statistical downscaling is it's an advanced form for analysis, and you can actually use that to diagnose the situation, but also diagnose the global climate models. The one thing that is important is that these statistical models rely on a stable relationship between a large scale and small scale conditions, so that there's no change over time in terms of how the temperature depends on the large scale conditions. But the same also actually applies to all models, because both the global climate models and the regional climate models make use of something called parameterization schemes, which upscale like processes which are unresolved. So it's the reverse, and that too could also be limited by stationarity as well. So it applies to all modeling. When it comes to empirical statistical downscaling, there are also three different sort of branches or different sort of strategies. So the first one is called perfect prog, which uses graded observations, or maybe even better, reanalysis to describe the large-scale conditions. So we call this the predictor. And then the local observations, say station data, or maybe even graded data as a predicted. That is the local scale. And it uses both these types of observations in the calibration of the downscaling model. This is quite different to what we call the model output statistics, which use actual model forecasts as predictor, and then local observations as predicted in the calibration of the model. And the advantage of that is that you basically will apply it directly to your model, but it will also be able to correct for some systematic model biases, and actually it will tell you whether your model is actually making a good forecast or bad forecast. And the third one is it's a hybrid perfect prog model output statistics scheme, and that uses a combined observational model simulations as predictor. We use something we call common UFs, which we will come back to in a second lecture, to actually represent these combined set of predictors. And then you use local observations as predicted in the calibration of this model. The nice thing with the hybrid model is that you also get projections or predictions at the same time, whereas in the perfect prog approach, also in in the perfect prog model, then you have to use that model. You calibrate it for observations. You have to apply that to the model, and you have to make sure that the model actually corresponds with the predictors that you used in the calibration of the statistical model. The model output statistics will of course also have the predictions in it as well directly. So the empirical statistical downscaling can also be applied in three different ways, in addition to the ones I already talked about. And one is the most common, which I call downscaling weather. So basically you take each point in time, say day by day, or say month by month, or even hour by hour, and you find a matching between the local observations and the predictor, and you apply some kind of statistical method to actually link the two. And this is typical for, say, model output statistics, and you can also use it for the others as well. Or the other alternative is actually downscaling climates. Basically, so you try to you try to predict how the probability distribution functions change. So, and you can estimate like the parameters for these probability distribution functions over like a period, say a year or a season. You have the, say, Gaussian distribution, so you have a mean and standard deviation. And then you want to know how these parameters change, because then you can actually predict how this shape changes as well. So then you work with aggregated data over periods, and then you, of course you can make a probability distribution function for, say, hourly data or 3-hourly data or daily data for say any variable, and then you try to predict how that changes. The nice thing about predicting how these probability distribution functions change is that you can make a use of these in weather generators, which actually may use these parameters as input, because they in the weather generators you often prescribe this kind of statistical characteristics. Of course, you can also get a change in these probability distribution functions from the downscaling weather, but then first you have to get the time series, and then you have to estimate these curves, whereas in downscaling climate you do it directly, and then of course you by applying this into weather generator, then you can go back into sort of the daily time series as you do here. So downscaling weather is basically the most common way to downscale. It gives you the day-to-day representation of the states, and often later you can use different types of methods, like the analog models or regression or artificial intelligence. When you go for the downscaling climate approach, basically we define the term climate as weather statistics over a given interval, or the parameters that define the shape of a probability distribution function, which subsequently can then be used to tune weather generators. The nice thing with downscaling climate is that statistical properties are often highly predictable, and this also is maybe more closely to the way statisticians often work, because they often look at the probability density functions and the probabilities. So then the methods you would use would be more like regression and artificial intelligence, because the analog model would not be suited for this. Then when it comes to making choices for downscaling, should I use dynamical downscaling or empirical statistical downscaling? And these two different approaches have different strengths and weaknesses, but they often complement each other. So my clear advice is to make use of both, because then you get more confidence if they agree. You don't have to make use of both for all the GCMs, but you should have some in common, and then you should apply the empirical statistical downscaling to all the GCMs you have. And here's one example showing that. So here you have, these are aggregated temperatures over Poland, and then you have the raw data here in yellow. And then you have empirical statistical downscale results in gray for all the models. So you can see that it narrows the range a little bit. And then there are 9 of these runs have been downscaled with a dynamical downscaling, or RCMs, in blue here. And then the same models in red have also been downscaled with empirical statistical downscaling, and also the same models here. The raw data are shown here as well. But you can see that the downscale results for the same models are quite similar, so they correspond quite well. But you can also see that in this case, these models are based on the Eurocordex data. They represent the lower range of the temperature projections in the future compared to the rest of the CMIP 5 ensemble. So this was, I think, the RCP 4.5. And then one important message here is the law of small numbers, because on regional and local scales there are pronounced variability that cannot be forecasted. So it has a very stochastic nature, and this is because internal variability is chaotic and it's non-deterministic. So it's more or less like by chance that you pick one model simulation that has like a high temperature or lower temperature. It might be the same model, identical model, which actually gives different types of realizations or different type of outcome. So if you pick a small number of model simulations or like a small ensemble, then you're likely to get non-robust and misleading results. And it's basically equivalent to working with a too small statistical sample. So I will talk more about this in the next part. So I will finish with some additional reading. So if you're interested in more learning more about downscaling, downscaling climate information, I can recommend this open access article on Oxford Research Encyclopedia. And also, we have a companion on downscaling. This is based on the empirical statistical downscaling, and is provided within this R-based ESD tool, which is freely available from GitHub. And then once it's installed, you can you have to run it within R, which can be installed from CRAN. And then the following code down here will actually download a PDF with a companion for you. Thank you.